Hello, everyone. So we have Angelos with us today, right? So Angelos is the head of the City Intelligence Lab at the Austrian Institute of Technology in Vienna, and he teaches at the Institute of Advanced Architecture of Catalonia and the Bauhaus University in Weimar. He studied architecture at the University of Patras and computational design at the Bartlett UCL, and he has completed his PhD as a Marie Curie Fellow at the InnoChain Innovative Training Network. He has previously worked as an associate at Foster & Partners, and he has been teaching at the Bartlett UCL, the UAV in Venice, and the TU Graz. His research focuses on performance-driven design and simulation, but he has worked in various fields, including AI and machine learning, AR, VR, 3D scanning, digital fabrication, and interactive installations. He has developed various design systems and simulation interfaces, including InFraRed, an AI-based design framework for urban planning, which he's going to present to us today. Right? Thank you for being with us, Angelos. The floor is yours.
Thank you, Mihaly. I would like to first of all say hi to Pavlos as well, and thank you for the invitation. It's great to see this course. I've heard a lot about it, and I was always curious. I'm an architect. I studied architecture, and I studied in Greece. Truth is, I didn't really like architecture that much, and that's why I tried to find a way out of it, and that's how I ended up doing research. And maybe this is like a kind of like a let's say justification of why what I'm doing is not like that much architectural. But anyway, so I've worked on different things. I was working at Foster's for 6 years, for 5 years at Applied Research and Development. I think you've met or you're gonna meet Marios Tsiliakos, my friend from there. We used to work there together, or Martha. So a lot of things that are like I'm gonna show come also from that era, like sort of say like the parametric design kind of like paradigm that started like emerging like 15 years ago. That's how I know Pavlos as well, and Michalis and Odysseus. So I've been like doing most of my kind of like life research on architecture, and mostly simulation. So integration of simulation and performance feedback for design. So like essentially, how do we connect simulation systems and models to architecture, to design? And it has been in different fields, like including digital fabrication. For example, like we worked in IEC a lot with, let's say, clay, 3D printing, and all those sorts of things that I could talk about. But I want to actually speak in this lecture about the work that I've been doing most recently. And that work is all urban scale. So it's like all about urban planning. So it might not be like as interesting, but I think that what I want to say before I start is that it all applies. It's exactly the same principle that applies to also the smaller scale, the fabrication scale, or the building scale, the design scale. The idea is how to somehow create more intelligent design systems by integrating performance, by integrating simulation models and analysis to them. So yeah, the lecture is called Intelligent Framework for Resilient Design, but that's like kind of like a framework that we've developed, but I'm going to get to that later. First of all, who we are. So as I said, like I was working in London at Foster's, then I moved to Barcelona, did my PhD. But since a couple of years now, I'm in AIT, and you probably don't know AIT, but it's the Austrian Institute of Technology, which is essentially, I've learned this to say it by heart, the largest non-university research organization in Austria. Doesn't mean much. It means that it's like big enough to have funding to let us work on research and like do things that we're interested on. It's co-funded by the so it's like a state organization like Republic of Austria, and also the Federation of Austria Industries. It's actually a great scheme because we are integrated in the industry. So we like actually working on projects. Like most of our work is contracted and like project work, but we also have funding, like base funding, to do like fundamental research. And a lot of the things that you'll see today here is actually funded by the AIT to kind of like advance, let's say, computational urban planning, so to say. Projects all around the world, from India and Kazakhstan to Brazil and like Ethiopia. It's an interesting kind of like place to work, because we get like there's a lot of things that we're doing. It's not like, of course, the computational urban planning is like just one small part of it. Most of it is like transformation and resilience. urban transformation and resilience. And that includes, of course, smart cities and energy and resource management and like water management and waste management and all of these things, preparing for what's inevitably coming. So climate change and urban resilience and how you react to all that. And the kind of like going into more of the part that the lab is working on, urban analysis and simulation, a lot of work on how do we analyze cities and kind of like simulate conditions and understand cities better. And of course, computational urban planning, so like generative, so there's a generative side of things. The lab itself, it's kind of like built as an idea of like an interactive interface for the simulation and the modeling and the the computational urban planning. So it's got a lot of interactive interfaces and mixed reality and AR, VR components. And this is how it kind of looks like when we're pretending to be working on something and people take pictures. This is like how the city intelligence lab looks like. There's like augmented reality models and there's like, interactive screens and stuff like that. This is a little bit like, how it is. If you ever come to Austria or Vienna, I think you might do, please feel free to come and visit us. It's great to have always guests and show them around, because actually it's an interesting space. Right now, we don't allow anybody in because everybody is potentially going to kill us. So we don't allow people. But once we get vaccinated, we will be happy to get you. Anyway, so a little bit about this project that I was talking about. So the City Intelligence Lab is also very closely related to the Cognitive Urban Design Computing, or CODEC project, which is essentially an internally funded AIT project that like funds the research of a few PhDs and a few master's students in order to advance the computational urban planning. And most of the work that you see and you will see is part of CODEC. And CODEC is also led by Reinhard König, professor, University of Bauhaus in Weimar. So we're together working on the lab and the CODEC project. I'm like the deputy on the CODEC and the head of the lab. So enough with that, and let's go to the actual interesting stuff. Who knows what this is from the audience? And please like speak up if you do. I hope at least someone knows what this is. Pavlo, I was waiting for you to say something. No? Anyway.
I'm here, man, but
you don't know what it is. This is generative components. This is like GC. The first GC. This is GC. Like this is the beautiful GC.
I thought you meant a project. It was not.
No. GC. Okay, GC, and that was like 15 years ago, roughly, right? And so that was like how horrible like computational design was 15 years ago. But also, it was a kind of like a revolution. This is when I started like getting involved in computational design. It was like essentially learning GC. It was like a really weird system that was kind of like within MicroStation, and you could just like connect things. The same thing that you do essentially with Grasshopper today, but it was very, very crude and crashing all the time. 15 years forward, you have the kind of spaghetti that you probably have cooked very, very often during this course, which is what we have today, right? So we've gone a really long way in these 15 years. Like we've actually progressed quite a lot on what we can do with computational design. And this is probably something which is a little bit more niche than that. If we go again 15 years back on, let's say we have all this ability to create geometry and generate like design, which is like parametric or whatever you call it, like associative or whatever. But in order to connect that to performance, to actually understand, how well these designs perform, this was really, really difficult 15 years ago. This is a connection of GC to Ecotect, which was a very weird connection that you have to download. You have to download DLLs and run the sorts of like weird things on your computer to get a solar radiation analysis shown on your GC kind of like definition. It was not a definition, but it doesn't matter, on your GC geometry, right? And that was like a really big project and breakthrough or whatever. And today, of course, you go into Food for Rhino and you download, 20 different plugins, and you can do all sorts of things from kind of like FEA analysis to particle spring systems to CFD to all sorts of different things, right? So we've really progressed in terms of like performance feedback, as we can call it, like in design. Right? We've done a huge a huge progress. So that means that when we're talking about urban planning, we can actually have like a much more intelligent workflow for urban planning. We can integrate into the planning process all sorts of different KPIs and performance metrics, whether it's economic or climate or resources connected, right? And maybe we'll start with a little bit what we've done in the codec project. This is not really my work. It's before I actually started working at the lab. This is the coding spaces. I don't know if you know it or you've heard of it. It's a very interesting collection of computational analysis and generation tools for urban planning. It's a collaboration between AIT, the Bauhaus, which Reinhard has put a lot of work on this project, and ETH, and especially the Future Cities Laboratory, which is also in Singapore. So it's a connection. It's a network of people that have all worked together to produce this. It's a very interesting toolbox, and you don't know it, you can have a look, because it's a lot of it makes a space syntax metrics and other let's say similar tools available. So what you can do with that is find shortest paths and create centrality graphs or measure the typical, let's say, spatial metrics of space syntax. You can also generate things like streets. For example, in this case, you see how you can generate a street network from a plot. And you can actually do more interesting things as generating whole typologies and whole building blocks very, very quickly. So that gives you the ability to not really design iteratively, but essentially create generate solutions very fast. I'm sure you have seen things like that before. It's not really that new, of course. For urban planning, it's relatively new, this process, because it has not been adopted so much as in maybe building design. Here you can see you can build a whole neighborhood and change program and very quickly adapt, and that is it's already a step up. We're doing more things than that in the lab. I'm just going a little bit through through several things that we're doing, but also giving you an overview of how we can think of the computational urban planning sort of process. Here, what we see, if I start from the beginning of the video, we see accessibility or in a city, how much of the city is accessible through certain transport modes, so bicycles, buses, and trams, and things like that. And you can actually even design a sort of transportation line or a transportation system by adding a few stops, and then you can realize what you can access through that in a city. Of course, it means that you can load, of course, existing transportation systems and see how you can affect them by adding new stations or changing stations location, etc. Other things that we do is, as I said, a lot of climate simulation. So this is a simulation we've produced in the lab, which is a rainfall simulation. So this is a particle system essentially, which runs through the digital terrain model of the city, and you find you can follow the line of the easiest path that would follow the water would follow the same path essentially, and you can identify locations, as you can see here, for example, where you have a concentration of water, and then you can find buildings that have basements and other features that can be dangerous, and then you can create a resilience plan for them, identify places where you need to intervene before a catastrophe happens. But if we go back to this, so this is kind of a quick overview of things that we're doing, just a couple of projects. If we go back to this connection, so yes, today we have all these capabilities. We can connect all these different performance and simulation models, but the truth is that they take a lot of time to run. So if we take, for example, the typical duration in minutes of a study, for example, so solar radiation study is a very quick one, but for example, a wind CFD study, a wind comfort study, I don't know if you've ever done a CFD study, it's a computational fluid dynamics. It can take up to a few hours. It can take 5 hours to run, or an annual wind comfort study, which takes into account the whole year. It can take like, again, a few days, or same for thermal comfort study. So this means that if you were to do like, this iterative, let's say, performance feedback loop, so you can like want to run a few hundred options for a project, not just one, then it takes like a serious amount of time. So if you were to do, let's say, 1,000 studies, we're talking about like a generative model now, where we like run 1,000 different, let's say, options, then you get, again, even a solar radiation kind of like simulation takes 500 minutes, so it's like a lot of time. So, you can imagine that in a CFD, for example, project, it's almost impossible to run 1,000 CFDs that take 5 hours each. It's like 5,000 hours. Nobody has this amount of time. So that's exactly what we are trying to. That's where we started, actually, to tackle with InFraRed. And we started with the kind of like the idea of using machine learning models to essentially speed up or like cut that time to like near real time. So how can we take simulations and models that would normally take consume time to be performed, and kind of like use prediction to predict them in almost real time. So we start with this thing, which is a generative adversarial network. You probably don't know that, or you've never heard of that unless you've done a little bit of machine learning. But you might have seen something like that, for example. Slightly more entertaining. You take a horse and you convert it to a zebra, and that's automatically done because it takes lots of images of horses and zebras, and like or people who have like manually painted zebras on horses, and then learns how to convert them. It's the same kind of like logic that takes, I don't know, a photograph and converts it to a Monet, a Van Gogh, or a Cézanne, or a whatever like painting. If you haven't seen any of those examples, which are a little bit also more into the machine learning side, you might have seen this, and that's probably the kind of like the most well-known example of this kind of like technology, where you take your face and you make it look like your dad, as it's the case here. I do look like my dad weirdly a lot in this picture, and I think this is because it's there's a lot of like training of young old people behind it. So how is that relevant to us? This is, I think, the most powerful image of the project, because it shows like these are like two almost identical, let's say, images, but one of them is a simulation. One of them takes like 15 minutes to run, and the other is a prediction, and it's like instant. So one is like takes like a few milliseconds to produce, and the other is like it's taking 15 minutes. And this is where we started. How we did that is we took, let's say, the city. This is solar radiation models are specific to each city. So we took the city of Vienna in this case. Took all of the kind of like models that we had from the city kind of like planning department, and we ran thousands of solar radiation simulations. We took all of these solar radiation simulations and we trained a neural network to predict essentially this kind of like result. Here you see some of those results. So you see like the input on one side, and then you see on one, like on the middle, you see the simulation, and on the right side you see the prediction. And we were really happy with the result because they're performing really well, especially the solar radiation model. That's why we show it first. It really performs very well, almost 95% accuracy, which is really great if you think of the gain in kind of like the time consumption. And this is, again, solar radiation, but like in a zoomed-in version. It works in different scales. That's what we're trying to show here. But if solar radiation is like, let's say, it takes 15 minutes, something you can actually do today very quickly. You can make, hook a kind of like Ladybug tools component, and you do it in almost no time. A CFD simulation is a much more complex and very, very time-consuming simulation to run. Each one of these little tiles usually takes about 5 hours to produce, 4 or 5 hours to produce. So you can imagine like running 5,000 hours of simulation is a really complex task. We did it using the AIT infrastructure. There's a cluster, and we ran 20 virtual machines that were running for a week, all of the simulations. And at the end, we produced the results, and we trained the same machine learning model, and we were really happy with this result because it's really a breakthrough for us. We haven't been able to get instant, because again the time you need to predict this is again milliseconds. So we got instant CFD simulation, which was a breakthrough. Generally was very well received, and you can see again how well it performs. So what do we do with that? We've created like a sort of started with a simple parametric model, and we can change parameters from here and there, and we can change the gaps between buildings or streets orientations or things like that. And you can immediately get like microclimate statistics for these kind of like for this example, right? You see here, like I changed like the center plot or whatever, and I get like an immediate prediction on how much percentage of my urban area is within certain thresholds. For example, the optimal wind speed or the optimal temperature of this area, which is very promising because you can actually design, and you already know immediately know what like your the effect of your massing is on the thermal performance of the quarter. Of course, we didn't stop there because it was really interesting. We went into other kind of like dimensions of performance, which is like related to, as I said, like accessibility of transportation or walkability or a noise, which was also very important, or other things. We're not going to go into everything here. I just want to show you like how this project evolved. So we started like as a kind of like a little bit of a research project. Let's do machine learning to predict, and then let's do a parametric model, and then we actually did a whole kind of like, let's say, framework. That's what InFraRed started like being born. I hope the sound doesn't go through because it's a typical funny sound for videos, for promotion videos. And here it's like where you see like a little bit of an overview. I'm gonna go into detail of how, let's say, InFraRed as a kind of like framework works. So here you can see essentially, I'm gonna go through it in more detail from here. You can see in a project, for example, this is a waterfront redevelopment in Sweden that we worked on a little bit, which to pitch a little bit of a project there with Link Architecture, a company that works in Sweden. So we put together all the things that we're doing in InFraRed in that time. That was like about 6 months ago, and we kind of like did a little project. So here's the massing part. So again, using all the generative aspects of our tools to produce very quickly geometry. So changing like the streets essentially immediately changes the massing, and then you can have like this like attractor points, and you can create or add or remove density. Not very kind of like interesting stuff, but this is more like the thing that we were saying for like. Here's where you have like a module where you can see like the wind performance, and you can see actually how different days of the year, different like wind speeds, how well they perform, and you can do it very quickly because you can change like the parameters, and you can immediately see the result. You don't need to run the simulations anymore. You see the results immediately in real time, and that means that you can actually start, as I was showing before, you can start playing with design components. For example, you put a park somewhere, and you can see how the wind goes through very quickly, and you understand like what happens if I put the park on this plot or on this plot. How much of the area that I'm generating is a comfortable, because there's a lot of wind in Sweden and the waterfront, of course. And you can see if I can block, let's say, certain streets by buildings. How much do I make this better, etc. Or if I, let's say, knock off a few buildings, or if I add the towers or things like that. All of these kind of like things were impossible to do without the machine learning, because you for every iteration of this you need like to run a 5-hour CFD simulation, which is really not feasible at all. So it really changes the way you're designing, and it changes also the cognitive ability of the designer itself, because the more you see that, the more you will understand what like a tower does to a kind of like a plot. So then you do it enough times, you will, as an architect, as a designer, also develop a certain cognitive capacity to understand, to be able to design with the wind as a component. And that's kind of like, I think, the most interesting part. Of course, as I said, we didn't only use wind simulations. Maybe that's the most kind of like impressive part, but of course we used a lot of space syntax measures. This is calculating accessibility, so to parks or to like retail In the same model, it's all integrated, and this gives the ability to, I'm going to go through them a little bit faster because it's a little boring. It gives the designer the ability to have like an overview, to understand like every kind of like design decision, what it does into all of the other kind of like performance aspects. So in this case, for example, designing a bus line that goes through the quarter, through the neighborhood, and then see how much, you know, the walking time to stations change. Similarly here, you can see the potential of passengers, and of course noise and other things. You see how many, you know, how much of your population is exposed to noise pollution, etc. We have actually gone a step further after that. We wanted to actually open up this kind of like model to as many people as possible. So we created a web interface. So it's actually, I'm gonna type the location, the URL here, and you can actually go and test it yourself. This is, you can just type your like location, and you can just select your wind direction, wind speed, and it actually runs a 3D CFD in real time. So you can actually test it for yourself. I'm not sure where the chat box is. It's here. So I can, yeah, very quickly. I'm not sure why the video stops when I try to type, but yeah, that's where you can go to see that. It's a website, like, it doesn't take too much traffic. So if you see like an error, just try it a little bit later. And then of course we implemented all of that within the lab's kind of like interfaces, and that's like a little bit of a promo video. The other thing we did, we got, when we actually started presenting this to the world, we got a lot of interest from different parties. And in this case, we got Giraffe. I don't know if you've heard of Giraffe. It's an online platform for design. So you can actually use it as a kind of like an online design tool, so to say. And we were asked to integrate the wind comfort like model there. So that's exactly what we've done here. We changed a little bit the interface, and we also added a few features. So here you can see, for example, the Lawson's criteria, which means like, you know, how much percentage of your area is, you know, good for sitting, good for standing, whatever. You can actually select specific wind speeds and see them on your, let's say, design area, and see where they occur, and some other, like, you know, more informative things. And again, the idea is that you can actually kind of like interactively design with the wind. You can like rotate buildings or like block certain areas, and again, you get a, let's say, a metric of how well you're performing, which was also quite well received. If you want to use InFraRed at some point, let me know, because we can get to students, we can get free license to Giraffe, and that's, or reduced license. I'm not sure exactly how they're doing that, because it's a paid service. But we're also planning to release InFraRed like soon as a kind of like online tool, online design tool. But this is like a little bit like, not, it's you know, hot off the press, not really there yet. So then if we go one step further, again, we understand we can do all of these kind of like interactive, you know, design with, you know, wind and solar radiation, all of these models. But it also means that we can, instead of like, you know, running these iteratively and interactive models, we can also run like, you know, 1,000 different iterations. And then, I mean, I'm sure you've seen Design Explorer before, and then you put them in Design Explorer, and you can actually start exploring your design space without like, you know, explicitly designing, but like just like selecting, let's say, certain parameters that you're interested in, or certain performance metrics. So in this case, you're selecting a certain amount of FAR and rotation, and then you see what kind of like percentage, what kind of like, you know, what part of my design space satisfies certain performance criteria, like OSR, or like performance criteria could be also spatial metrics, but also wind speeds and things like that. And you can rate solutions, you can share the same kind of like design space exploration with other people, etc. So again, this was not possible without, so like you can't really do that without a machine learning backend, because it is impossible to run 1,000, you know, CFD simulations for a project. Same thing we're doing. This was a paper we presented at the CMOUT conference in Simulation Urban Design, Architecture and Urban Design conference in 2020, which was again taking a quarter and like running thousands of different options, or like iterations, and then analyzing them and kind of like optimizing the certain parameters. And then, of course, the idea is that you don't want to take away the control from the designer. So you can like start with an optimization process and can continue manually in an AR environment, or that's kind of like a little bit showing all the capabilities of the lab in one video. Yeah. And of course, the performance-driven design aspect is our main focus, but of course the kind of like bringing that all in a natural kind of like planning process, it's also important because essentially, especially for the urban planners, it's not really like common to work over like a screen and a certain like a design explorer sort of like statistical model. It's better if you work on a physical model. And so we've done a lot of AR, HoloLens, iPad, all sorts of other like stuff. Here you see the lab again in kind of like in its full capacity, and you see how we have designed like interfaces so that people can actually work with the physical model in real time and in real space as well, sort of say, and design the kind of like urban plan together and collaborative and also intelligently. So I think that's where I stopped, and here is our website. It's http://cities.ait.ac.at. I'm gonna actually click on that. It's going to change because we're about to revamp our website, but I'm gonna post it here just in case. So yeah.
Okay, thank you, Angelos, again for coming.
Thank you.
Thank you. Thank you. It's been a pleasure.